Hi, homeschoolers. Let's do the 3.2 lesson. The 3.2 lesson is still about exponential growth and decay, but now we're going to start to see more real-life applications of how we use exponential growth and decay when we're given like a rate of increase or a rate of decrease. So we're going to start off with our basic exponential equation, y equals a times b to the x power. So remember that a is still the initial value, right? The y-intercept is how we usually see that. And then b is the base. And that base is either bigger than 1 or it's in between 0 and 1. And that's how we get growth and how we get decay. So if that base were a 2, for example, then that would mean growth, because that would mean that the population is doubling every whatever amount of time. If it was a 3, then it would be tripling every amount of time. So that number that is right there is the number that is the thing that you multiply by, the rate of increase. Okay, but usually when we talk about rate of increase in real life, we talk about a percentage rate. So we'll say like it's increasing by 10% or it's decreasing by 25%. And so you'll see those phrases increasing by with a percent or decreasing by with a percent. So we need to make sure that we can write our base. Sometimes when they don't just give you the base, they give you like how different it is from 100%. So sidebar, if I were to say like increase by 20%, then the number that you're going to use is you're going to use 120%, because normal is 100%, right? And if it's increasing by 20%, then you need to use 120%. If I were to say decrease by 20%, then what you would use is, how different is that from 100? You put it as 80% because you would subtract it from 100%. So that means that this base is going to be adjusted from 100%, because 100% would be normal. If I put a 100% there, then basically I'd be putting 1. So what you're going to see today is you're going to see your model look like this. Oops, wrote that wrong. You're going to see it look like that. So right here, instead of having an A, it's still the initial value. But we use a P because P stands for principal. And principal has a few different meanings, right? We're not talking about Mr. Smith. We're talking about the starting amount. And that usually correlates with when we're talking about money. So the principal amount is that first amount that you deposit. Okay, so then R would be the rate, and it is as a decimal. So if I give you a percent, you need to make sure that you're changing it to a decimal by moving the decimal over 2 places. And then instead of X, we often use T because these problems, the exponent is referenced to time. So it is the same equation, we just use different letters to show the adjustment of the kind of problems that we're doing. So here we go. Example 1, is it growth or decay? Find the constant percentage rate. Problem A. Y equals 782,248 times 1.014 to the t power. So we're not sure what this is about. This might be the population of a town. It might be like the number of bunnies on a farm. We don't know. But we do know that the starting amount is 782,248. So that many bunnies or people or whatever. This right here, this whole thing is the base, that 1.014. But they want to know, like, is it growth or decay? And remember, you're looking, is that bigger than 1 or is it in between 0 and 1? So since that base is bigger than 1, we know that this is growth. And then when they ask us the constant percentage rate, they're asking us how different is that than 1? So see that 1.014, that stuff in the parentheses, is in the same spot as up here when it's in the parentheses. See how it's being adjusted from 1? So what it's asking you is how different is 1.014 from 1? And in this case, the subtraction is really easy. Like, I'm really hoping that you don't need to use a calculator to tell me that it's 0.014. But that's the decimal version, because in the formula, when we actually do math, we use decimals. But they asked you for the percentage rate. So what is 0.014 as a percentage? You just need to move the decimal over 2 places. Boop, boop. So that equals 1.4%. So if I were asking you to build this model instead of like dissect the model, then I would say the population is increasing by 1.4%. And then you would be able to put it as 1.014. Let's look at B. A equals 1,300,000 times 0.9858 to the x power. Now, don't be alarmed by them using different letters. Remember, they use different variables for stuff all the time. This is like in the y spot. Who cares? And then up here, they used a t instead of, or an x instead of a t. Okay. Either way, we're looking right here. This is the base. Is this base bigger than 1, or is it between 0 and 1? Well, this one is in between 0 and 1, which means that this is decay. Okay, so now you need to figure out how different is this from 1. So you need to subtract 1 just like we did up here. And when you subtract 1, of course, you're going to get a negative number. So you're going to do 0.9858 minus 1. And you might need your calculator for that or not, but you get negative 0.142. Looks like I forgot a 0, huh? There we go. Snuck it in. Okay, so we need to give that as a percentage. So again, you're going to move the decimal over 2 places, and you're going to say negative 1.42. So that negative percent is a pretty good indicator that it's going to be decay because it's decreasing over time. That's why you got a negative percent. All right. Here is example 2. Determine the exponential function with an initial value of 8 that's increasing 3% every day. Okay, so we're going to be filling in this model, right? We're going to put the initial value right in front of here, and then inside where the base goes, we're going to be either adding this 3% or subtracting this 3%, depending on the problem. So it's increasing, which means that we're going to add the 3%. But remember, R needs to be a decimal, not a percentage. So remind yourself that you're going to need to move the decimal over 2 places. So 3% is the same thing as 0.03. So it says initial value of 8, that goes right here. And then inside 1 plus 0.03, and it's to the t. So I would write y equals 8 times 1.03 to the t power. I don't need you to show me the step where you add or subtract. I assume that you know how to add and subtract numbers. All right, So now we have some common rates. These are the ones that we see all the time. You know, like 20% increase happens sometimes, but it is not like wicked common. The ones that are super, super duper common are doubling and halving. Halving, I feel like I should pronounce the L more. So doubling happens all the time. We often talk about like how like this doubles at a certain rate, or same thing with cutting in half. Ooh, this cuts in half every however many days. Okay, so if you're going to double, that means that you're going to add 100%. If it's increasing by 100%, 100% plus 100% is 200%. So that means that your base would be 2, right? So if you were to see it, you'd be like 1 plus 1, because 100% plus 100%, and then to the t power. So when we see a doubling equation, we know that we're going to have a base of 2. And you knew that a couple days ago. I'm just reminding you why it works. Okay, now up in the exponent, I want you to put the t, but then I want you to divide that t by doubling time. And I'm writing it really small because it's all up there in the exponent. We're going to talk about that in just a second. But let's talk about halving. So that was doubling. Now, when you cut stuff in half, that means that you're going to take away 50%. So the equation inside would look like 1 minus 0.5. Right? If you're going to take away half, then you're going to take away 50%. So that means it'll end up looking like y equals p times 1/2 to the t power. But again, I want you to divide that t by, oops, this time it's halving time. Okay, so why did we divide the t by something? Notice in example 2 how I say that it increased by 3% every day. So that means every single day you'll see that 3% increase. But what if I did every other day? Then you wouldn't just, if I told you that t was 8 days, you wouldn't put an 8 up there because it didn't increase 8 times. It only increased 4 because it was only happening every other day. So if something doesn't happen every one, then you want to make sure that you put how often it happens, like you take that t and you divide it by. So for example, let's say I say, this happens every 3 months. How many times does it happen in a year? Well, if it's only happening every 3 months, then you're not going to put a 12. It's not 12 months for a year, because it's only going to happen 4 times if it's happening every 3 months, because 12 divided by 3 is 4. So most of the time, the doubling time and the halving time, that number that you divide by, is 1, because it happens every 1 year, month, minute. But if it's different than 1, then you're going to put a number there. Let's do an example. Example 3, a culture of 200 bacteria is put in a petri dish and the culture doubles every 2 hours. Predict when the number of bacteria will be 250,000. Okay, so when we write out that equation, we're starting with 200, so that goes in the initial value spot. And it says that it's doubling, so automatically I know that my base is a 2. Okay, and then I'm going to raise it to the t power, but notice it doesn't double every 1 hour. It doubles every 2 hours. So I need to divide that amount of time by 2. So if I had said it doubles every hour, then you would divide it by 1, so it would just be a t. But since I said it doubles every 2 hours, you need to divide that amount of time by 2. Okay, so I want to know when it's going to equal 250,000. So I want to know when y equals 250,000. So what I want you to do in your calculator, either Desmos or like your actual graphing calculator, I want you to put one side of this equation on one line in your grapher, so y1, and then the other side of the equation on y2. And again, it doesn't matter which calculator you use, they both are perfectly fine with this. So I'm going to type it in. I'm going to use Desmos this time because I've been using the other one a bunch. Okay, 200 times 2 to the power of, and I got to use an x because the calculator doesn't use t divided by 2. Okay, so I want to know where these two things touch. And right now I don't see it because y equals 250,000 is way up here. So I'm going to do some zoomage. On a physical graphing calculator, you would just change the window, right? All right, here we go. Oops, I need to put a y equals. There, it'll graph that line for me. Okay, so I see them touch way up here. I'm just going to put this on my grapher. I've got like, I want to find that spot right there. So on Desmos, I can just touch it and it'll tell me where it is. That is 20.575. On the physical graphing calculator, you have to find the intersection. We only need the x value. The y value is going to be 250,000. Okay, so 20.575 is in hours. So that's my answer. T equals 20.575 hours. In this case, can you have partial hours? Have partial hours, so that's okay. If it was like an answer that was number of buses, then no, you wouldn't give a decimal. All right, let's one more. Example 4. The half-life of a certain radioactive substance is 24 days. There are 210 grams present initially. When will there be 2 grams? So half-life means like how long it takes for the substance to cut in half. And that's often used with radioactive substances and with other elements, like carbon dating is really important. They know how often carbon-14 cuts in half, like how long it takes for the amount to be half of what it used to be. And that's how they tell the age of fossils and bones and all that kind of jazz. Okay, so half-life just means how long it takes to cut in half. So this particular problem, again, we're going to fill in this jazz here, right? So since it's this one is about half, we know that the base is a half. We also know P is 210 grams. And we don't know T because it says when, so that's the thing we're supposed to find. Now, this needs to be a T divided by 24 because it doesn't happen every 1 day, it happens every 24 days. And we know why because we want to know when it equals 2. All right, so again, I'm going to plug this in for y1 and I'm going to plug this in for y2. Those of you that have an older graphing calculator, like when you hit the exponent button, it makes that actual caret on your screen. Don't forget to put this in parentheses or your calculator won't do it correctly. So this time I'll do it on the other calculator so you can see the difference. Okay, so on one of the lines I'm going to put 2, it doesn't matter which one, and on the other line 210 times 1/2, oops, 1/2 to the power of x divided by 24. Now, again, if yours doesn't show superscript, then you're going to need to put parentheses around the exponent. I can put parentheses around it too. That doesn't hurt anything. So if all else fails, just put parentheses. Okay, so now I'm going to graph it, but I'm going to adjust my window a little bit. Oops, window. I don't need to see all the way up to 850. Let's see. There's that flat line. And I don't see the other part of the graph yet, which means I must not see out far enough. So I'm gonna, like on Desmos, you can just pinch the screen until you see stuff. But on here, I gotta just be a little bit more deliberate. So I'm gonna go out to 500. That might be way too much, but we'll see. Ooh, there it is. Where is that spot right there? So I'm gonna make my calculator tell me. Second calc, option 5 for intersect. First curve, enter. Second curve, enter. And then guess I move the blinky spider over to where they touch and I hit enter. And my calculator tells me 161.142. And again, this is time. Time can be partial, so this is in days. All right, and that's the end of this lesson. Go ahead and take your 3.2 quiz.